thanks to the many industrial affiliate sponsors who support our lab and have kind of followed us in the mmWave world, and who are also encouraging us to look at this great future to terahertz and beyond. If you're aware, we have a great seminar series. I'll talk about that in a minute. I'm unable to, there we go. Yeah, I'll talk about that now. We have a seminar series we've put together. We just had the second seminar speaker just moments ago finish, Joseph Jornet from University of Buffalo. It was supposed to be live, but apparently they could not broadcast it live today at 11. It will be posted on the web shortly. They had some technical difficulty. I apologize to some of you who were trying to tune in for that. Hopefully that won't happen again, but that'll be up on our website shortly. But we've launched this Terahertz and Beyond series focusing on circuits to bring some of the world leaders to campus. And we've had a couple of great days already with Aydin Babakani at UCLA and Joseph Jornet, who's here today. Really exciting. But this gives you an idea of some of the topics and some of the fundamental breakthroughs that are happening that will make terahertz a reality, and I think earlier than many of us would have thought a few years ago. So when we talk about millimeter waves and terahertz, it's really good to put everything in perspective on where they are in the frequency range, the physical size, and how they look. You think about the microwave region, where we're talking about hundreds of megahertz to a few gigahertz. The wavelengths are on the order of tens of millimeters, centimeters, and the frequency range is like 10 to the 9th gigahertz. Really the size of butterflies if you think of a physical size. But as we move up to the millimeter wave and terahertz regime, we start to look at frequencies that are now on the order of hundreds of gigahertz, 10 to the 12th in frequency, 1,000 gigahertz, where we're talking about the size of the tip of a needle. So these wavelengths are very, very small. And what's interesting is the temperature at which an object radiates the most intense for the particular frequency. You look at the human body at room temperature at 100 to 200 to 300 Kelvin, say 300 Kelvin, it's smack dab in the terahertz and even just above the terahertz region, moving into the infrared. So we're really, terahertz is kind of this magical frequency. We don't know a lot about it, but it's when we start to get so small in size where temperature of objects where this radiation most intense, the human body emits terahertz kind of naturally, and it's so small. And that has advantages and disadvantages, which I'll talk about in this talk. Now, those of you on the call are very familiar with this. The Spectrum Horizons initiative by the FCC earlier this year is looking to make spectrum available and to help provide huge amounts of spectrum, more than we've ever seen before in the history of the world, over 100 gigahertz of spectrum for licensed point-to-point, and looking at 15 gigahertz of unlicensed devices. The FCC has proposed this. Experimental licenses are now going to be, they're seeking comments and looking to make experimental licenses available from 95 gigahertz to 3 terahertz. That is huge because the FCC really has never looked before 95 gigahertz before. It's really kind of been an off limits. NASA has a lot of the deep space probes, a lot of probes up above the ionosphere in space, a lot of sensing. So opening up the spectrum 95 gigahertz to 3 terahertz, at least having that discussion is a very promising sign at the FCC. By the way, on the experimental license system, the FCC sought our advice, and NYU was really a leader in creating that fast licensing system. If you look at the spectrum band from 95 to 300 gigahertz, and I have a chart here, you can see that most of it is occupied by radio navigation and by radio measurement, satellites, radio location, really a lot of astronomy, a lot of radio astronomy, but there's a tremendous amount of spectrum here available. Now, the mmWave Coalition, of course, that's who we are on this phone call. We're looking at trying to bring some momentum to open up large contiguous blocks of spectrum, and that is key, large continuous blocks. If you go back to this chart, you can see that there aren't large continuous blocks. We're looking to open up some of these and be able to find some usage and make some spectrum available for unlicensed and licensed. Of course, everyone on this call knows this, but this is a slide I'm starting to present publicly about our coalition. Now, we're not the only game in town, this mmWave Coalition. A lot of other countries are out in front of this mmWave and terahertz regime. In fact, in Europe, they've really been much more out in front and are much more open about the dialogue of having frequency bands available from 50 to 300 gigahertz. And they've already earmarked a number of frequency bands that they're looking at. The traditional bands, which are in the mmWave range, as long as E-band, V-band, and this is on the agenda at ITUR for WRC19. In 2019, agenda item 115 is going to be considering land mobile and fixed services in the 275 to 450 gigahertz range. And both Asia and Europe have really been kind of unified in this, so it's appropriate that the mmWave Coalition get active and try to give some guidance to the FCC to see if we can get some global harmonization. One of the first mmWave to terahertz band transitions that will likely occur is moving up to D-band. While D-band is not a terahertz frequency range, technically terahertz is 30 to 300 gigahertz, terahertz is being used commonly for things above 100 gigahertz. So if you look at the D-band 110 to 170 gigahertz, this is really, you can think of it as the first terahertz band, even though terahertz technically is only 300 gigahertz to 3 terahertz. But there's a lot of spectrum in D-band. You can see that D-band is used by radio astronomy, radio navigation, satellite, but there is spectrum here for mobile in D-band. And one of the nice things about D-band and the frequencies at 140 gigahertz and up to 240 gigahertz is that the relative attenuation, the attenuation in air due to the molecules, the water molecules, air vapor, there's very little attenuation beyond the normal free space path loss. So there are regions in the sub-terahertz region where we can do really mobile communications. And as I will show shortly, we can do mobile communications even better than we do today. And I'll get into that. Now, there are a couple of really good papers, the overview papers on terahertz, some of the experiments that have been done over the last decade. And on the left, you can see the water vapor chart, the attenuation chart due to oxygen in air at different, you can see at different levels of humidity, and you can also see for different distances. And there have been both indoor and outdoor measurements made experimentally all the way up to 700, 800 gigahertz. You can see that we're talking about distances that are either sub-meter or distances up to several kilometers in outdoor environments, up at carrier frequencies of 100, 200, even up to 400 gigahertz outdoors. And of course, as I'll show in a minute, when you go up to these higher frequencies, these kind of distances should not be surprising, even with the difficulty of making power sources, because there's huge advantage to high gain antennas. And we'll see that how those high gain antennas can actually overcome the path loss. And if you notice on the bottom left curve, the attenuation, the gaseous attenuation in the atmosphere, indeed has many peaks and spikes, but there are some good zones in the 200 to 300 gigahertz region where you'll only lose 10 dB more per kilometer due to free space, due to the oxygen, meaning that over 100, 200 meters, you're only going to lose a couple of dB extra over normal propagation. So there's some amazing places that we can operate up to several hundred gigahertz for cellular, mobile, point-to-point, wireless replacement for backhaul. Very encouraging. And the data rates you get when you go up to these higher frequencies naturally increase because of the greater bandwidths available. We go up to terahertz and these high hundreds of gigahertz frequencies because there's more bandwidth. And you can see that the achievable data rates versus carrier frequency on the right are enormous. We're talking hundreds of gigabits per second. And you think about a fiber optic cable, and we're starting to talk about true fiber cable replacement over the air. What's interesting is to implement these high data rates, we can have an optoelectronic approach using optics, or we can have an all-electronic approach. Some of the optical approaches involve using lasers or optical signals and beating them, mixing them with another laser signal, very close in frequency at the optical layer, which is very wide apart in frequency down at conventional. And this is how we can make several hundred gigahertz sources. There's a lot of power inefficiency in going optical to electronic. But we could actually build oscillators and modulators using optical electronic components, and by mixing two optical frequencies that are 50 or 100 or 200 gigahertz apart, we can create very stable, very powerful modulators and mixers and signals to enable these hundreds of gigabit per second transmissions. Now at NYU Wireless, we've built a broadband channel sounder. You can see it on the left, thanks to our industrial affiliates who have supported this work, namely Keysight and National Instruments. They've both given us a tremendous amount of equipment, have supported the development of this gear. Virginia Diodes is on this call as one of our vendors. You can see we have Virginia Diode radio heads on the left and right, and these are basically front ends, and we mix down to about 25 gigahertz local oscillator. This slide keeps wanting to go forward for some reason. There's some timing set in it, I guess, Adam. I don't know why it wants to jump ahead. And three of my graduate students are on the right, Yun Xiao, Shihao, and Ojas, who are working on various applications of this 140 gigahertz band that I'll present in a little bit. We've just published a paper. It appears publicly in the Global Communications Conference, and all of our industrial affiliates, of course, see this work well before it's ever published. But here's some details about the channel sounder that we have. We basically have a wideband transmitter and receiver. We're using basically a simple dual conversion IF to IF system with 4 gigahertz RF passband. And we have really a commercial grade, 4 gigahertz wide RF transmitter, RF receiver with rotatable horn antennas. And we're using this now to conduct channel measurements indoor and outdoor. We could also modulate it, so we basically have a true transceiver. And this is a very powerful capability because we're able to take it into the streets of Brooklyn, the streets of New York City, deploy towers, and measure transmit power, path loss, multipath, angle of arrival, and build the channel models that will be needed for terahertz wireless communications. And here's some measurements we made. And by the way, we are behind on schedule on the measurements. We have a lot of measurements to do, and the students have started doing it every weekend. We're hoping to get outside before it snows. We're doing indoor now, but we've really got to get outdoors this fall. There's tons of data we're starting to collect. First, we're doing indoor because, as you'll see, there's some very exciting applications indoor with position location And we're also trying to understand how the environment would work up at 140 gigahertz. How different is it from 28 and 73, which will be commercialized soon. Well, first, here's a look at the free space measurement in a close area within a few meters. And I want to point something out that's very important to realize. In the industry, in academia, people are always saying the path loss is worse as you go higher in frequency. It's what you always hear. Things are lossy. And then you see a curve like this on the right, which shows that over short distances, indeed, you have more path loss at 140 gigahertz than you do at 28 gigahertz, right? Everyone thinks that. And that's because, I'll show the math in a minute, because there's this free space loss component in Free's free space equation that when you remove the antenna gains, that is, when you assume the antenna gains are 1, it's true, things are more lossy. But in all communication systems, we use antenna gains. And here's the math that shows, in fact, the opposite is true when you use antenna gains. When you use the area of the antenna and keep the area the same and go up in frequency, you actually get gain as you go higher in frequencies. If you look at the top, here's the free space equation. And what people always do is they peel off the lambda squared over 4 pi d squared term on the top. They peel that off. And that's why they say things are lossy as you go higher in frequency. But if you look at a physical antenna with an aperture, A sub E, and you replace the antenna gains at both the transmitter and receiver with the aperture, what you see is the lambda squared in the free space loss cancels out with a lambda by 4 in the antenna gains. And at the bottom equation, you see that it's not lambda squared in the numerator, but rather it's lambda squared in the denominator. You see this? I don't know if you're catching this, Adam, but it's the lambda squared in the denominator here. It was lambda squared in the numerator. And as lambda gets smaller, what this means is for the same physical area, your receive power goes up. Basically, your gain is increasing for a constant physical area. That's very powerful. And the world really doesn't quite understand this yet. You see, what that basically means is you can operate at higher bandwidths scaled by the area of the transmitter and receiver antenna, higher bandwidths for a given SNR as you go higher in frequency. So you're basically getting more bandwidth for free as we go up and keep the physical area the same over frequency. In fact, to show that here on the left, what you can see is if you assume on these bottom 3 curves that you have omnidirectional antennas at the transmitter and the receiver, which a lot of people assume, well, yes, indeed, your receive power is going to be stronger at 28 gigahertz than it is at 140 gigahertz. You can see there's about 14 dB difference from 28 to 140 gigahertz. There's about 14 dB difference here. However, if you assume one end of the link has an antenna area that stays constant with frequency, and then you just assume the other end of the link has an omnidirectional antenna, in other words, it gets smaller with frequency, then it turns out frequency is independent. You get the same received power at all 3 bands because you've kept one of the physical areas steady with frequency and you've let the other antenna be omnidirectional. But if you assume both antennas are omnidirectional, that is, you consider the area being constant at both the transmitter and receiver, you get 14 dB stronger received power at 140 gigahertz than you do at 28 gigahertz. This is very powerful. In other words, you get 14 dB, 20 times the bandwidth for free at the same operating signal-to-noise ratio. So you can basically operate with 20 times wider spectrum allocation at no cost to the signal-to-noise ratio when you use directional antennas. Now you have to find the beam as the area gets as the area stays the same and you go up in frequency, it becomes a much more focused beam, so you have to do beam finding and be able to lock those bore sight antennas together. But once you've got the bore sight aligned, you get this huge gain in the link. So going to millimeter wave and terahertz doesn't degrade your link, it actually improves your link. So going up higher is better. It's better for the future of wireless. Now, some things aren't better as you go higher in frequency. And here we've started to look at different materials. We've looked at glass, we've looked at drywall, and what you can see is you go up higher in frequency, common materials like drywall and glass, they become more lossy as we go higher in frequency. Clear glass is 3 to 4 dB loss at 28 gigahertz. It's 7 dB at 73 gigahertz, and it's 8 or 9 dB at 140 gigahertz. So there's a couple dB difference. We're looking at a lot of these materials now. We're really doing lots of measurements and getting more data for common materials as we speak. But understanding this is important so that we can figure out range and coverage and interference in Wi-Fi and other kind of indoor environments, and then we'll go outdoors and also look at the channel in this way. So it's going to be dependent on the material, but this is really great. We can use antenna gain to overcome the free space loss in omnidirectional systems. Now, to make measurements, to understand the channel, it's important to have a good methodology to make sure you're truly measuring the materials under test and not picking up multipath or measuring other items. So we've developed some standardized measurement guidelines that can be used by other researchers. We've published them recently at the IEEE Vehicular Technology Conference in order to do both cross-polarization discrimination tests to make sure that our antennas are working right, and how to measure cross-polarized discrimination so that we can understand what the channel does in depolarizing the transmitted signal, and also looking at how to do these penetration loss measurements. And it turns out there's some simple geometry based on being outside of the Fraunhofer region so that we can assume a plane wave, but also being such that our transmitter and receiver are not too far away that we're picking up multipath from ceiling or ground or walls. And so there's some very simple geometries that if you follow, you can be sure that you're measuring the true device under test or measuring the true antenna cross-polarization. And we verified these approaches by looking first at some cross-polarization discrimination with a number of horn antennas. This could also be used for phased array, patch antennas, lens antennas. But we looked at wide beam and narrow beam, 30 degree, 10 degree, different horn antennas. Here's at 73 gigahertz. We're also doing this at 140 gigahertz, where you basically take measurements of your antenna in kind of an open free space chamber. It could be a large room, it could be outside. And if you make the measurements over several close distances that are still in the Fraunhofer region, and you get the similar slope, that is, you get a slope over distance that behaves properly by free space, you can be assured that you're measuring the antenna and you're not picking up multipath components. And here's an example at 73 gigahertz with 3 different antennas where you can see we've measured pretty much a 28, 29, 30 dB cross-polarization discrimination. So we know with good confidence, because we recreated it over several close-in distances that are in the far field, that we can be sure that we are measuring an accurate XPD and not picking up ground bounce or reflections or artifacts in the system. Similarly, for penetration loss measurements, the same thing. You follow the geometry and you make several distance measurements close in but still far enough in the far field, and you make sure that the slope is correct. Got a little bit of a slight couple tenths of a dB at the 5 meter distance. This might be due to some Fresnel effects on the object that we were measuring, but still they're very, very small, within a fraction of a dB. So this is a measurement approach that you can use, and we use it for both polarizations and for cross polarizations. The student didn't show horizontal to horizontal, but we're making both horizontal to horizontal, vertical to horizontal, horizontal to vertical, and vertical to vertical. And you can see that we have penetration loss measurements, and you take the average of these and you can get a very good estimate, a measurement estimate of what a particular material will do. Now, what are some of the applications of mmWave and terahertz? Once you get up to this terahertz regime where the wavelengths start to become on the order of microns, you know, hundreds, tens of microns, there's a lot of things we can do. Now, we've known a lot about femtosecond optoelectronics since the 80s. There's terahertz time domain spectroscopy. Right now, there's commercial systems being used to test plywood, to test wood material to see how the glue has been healed. They're on factory conveyor belts. There's certain spectroscopy signatures that you can get from particular materials, from being able to detect fissures, cracks, efficacy of coatings to make sure they give a proper spectral return when hitting it with a broadband signal. There are also components that have certain resonances, and by using terahertz imaging, you could basically excite the resonances, see the energy produced back from the resonances, the vibrations. So you have this amazing spatial resolution due to the short wavelength. You're able to use that information along with other methods, say visual imaging, and you could basically use, if you will, frequency fusion, use terahertz spectroscopy along with other known things, visual or microwave response, electrical response. There's a way to do identification of materials this way. This is used commonly to detect explosives, to see how material is being used by terahertz imaging. Now, there's some disadvantages. Relatively long acquisition time, given the huge bandwidth, given the number of antennas often used to try to get a sufficient link. It's hard to find the focal plane when you have such tight resolution. How do you aim the focus? Because we're talking very, very tiny wavelengths, very huge bandwidths. And active components are a challenge. They're expensive. They don't really exist today. So you're dealing with passive signaling, passive monitoring, and that's very, very low power. It's very hard to get the signal levels needed to be able to get enough response. So getting enough power out to be able to do signal processing is a challenge right now. Well, in medical imaging, there's some very exciting applications, and already a couple of our speakers in the NYU Circuits, Terahertz, and Beyond seminar series have given us some insights into some of the very exciting medical imaging capabilities. When you get below the millimeter wavelengths, you start to see that you're talking about a place where we can basically put energy in and see what comes out, looking at the cells as lenses, looking at the cells as structures that give us insight into what's inside. The cell size is less than the wavelength, and the terahertz signals pass through the tissue and basically can create this scattering. The cells are impacted by the terahertz radiation, but the atoms aren't broken up, but they're kind of shaken around. There's actually movement. And this movement gives energy and gives various ways that we can detect what's happening. You can do time domain spectroscopy with coherent detection, and then you can measure the absorption coefficients and the refractive indices, and you can basically, based on the categorization of the refractive indices, make decisions about what's happening. Tumors will have a different response than healthy tissue. Different parts of the body have a different refractive index. They will reflect and pass energy differently. In fact, if you look at tissue characterization in polar liquids, there's high absorption when the atoms are arranged in a polar fashion, and fatty tissue has fewer polar molecules, and therefore there's going to be less absorption. There's a lower refractive index. Kidney and liver tissues have a much higher absorption coefficient, absorb the energy much more. And in tumors, the absorption coefficient and refractive index are higher in tumors. They're more solid, like solid organs, like kidney or liver. So we can get a lot of information out from terahertz transmissions in the body without causing the breakup of atoms in the valence shells, which lead to unstable atoms, which can lead to cancer. We're not at the energy level yet where the energy from the radiation is sufficiently large that it can break an electron out, which leads to instability. It shakes them, but does not break them. Now, one of the exciting applications in the wireless world, when you go up to terahertz, when you're up at these frequencies, where the wavelengths now sub-millimeter wave, is there's a huge amount of bandwidth, and there's also the ability to make very, very directional antennas. So we can start looking at, and we need the directional antennas to be able to get the link margin. We saw how by getting the directional antennas, we'll get more and more bandwidth for free without losing the signal to noise ratio. So you can look at many applications of indoor positioning, smart factories, IoT, see in the dark, using imaging to basically look through walls, get pictures almost like an X-ray, but without using the mechanism of X-ray, looking at the response back from radiated energy to see what's happening in the channel. These benefits, wide bandwidths, sparse channels with narrow beams, we can estimate the angle of arrival in a handheld device or in a base station. So we could start using this indoor, and this doesn't have to be indoor positioning. I should have just said mobile positioning, because this applies outdoor too, and I need my students to think broadly. They put indoor, but it's outdoor, indoor, it's wherever it is. And that's why the outdoor measurements are so important and why we're doing it, because these same ideas can work outdoor, but we're doing it indoor here for the next few weeks before we move outdoor. But the bottom line is we have these wide bandwidths. You can find the angle of arrival and angle of departure, very narrow beams. It's sparse. So this could be a feature. Is this showing up on the slide, this thing? Okay. So, so you basically can see you can really add this kind of positioning and it will come for free in future wireless systems. One of the ways to do locationing is to use what's called angle of arrival based positioning. There are a number of methods used where basically you figure out the angle between beacons of known a priori location. You figure out the angle. You can imagine spinning a rotating electrical antenna or having a phased array. And as I'll show shortly, imagine being able to receive energy from all angles of direction simultaneously. You could be looking for sources and figure out where you are. The other way to measure that's been looked at, and there are many, many ways, and we've published a paper at GlobeCom. In fact, you can see down here are some of the citations of the GlobeCom paper. Well, no, I don't know where the GlobeCom, there it is. There's a paper we have coming out of GlobeCom where the student looked at signal strength positioning based on a simple distance-based signal level law. The farther away you go, the signal gets weaker. This is a very crude model, but it turns out you can find the maximum likelihood at any particular distance for what the signal should be, and you fuse that with path loss and angle of arrival, and it turns out you can do remarkably well. Here at the NYU Wireless Center, we have about a 30 by 40 meter floor with cubicles, and looking at simple fusion, just a first iteration. We have a lot more work to do on this, but a very simple iteration, you can see that we're able to get within a couple of meters accuracy using a number of base stations and with measurements we made at 28 and 73 gigahertz. This is very encouraging because we're not even trying to get position location. We're just using the measurements we've made and just seeing how a couple of different algorithms might work. So there's a lot more work we can do, but this gives us a lot of confidence that position location will be able to come for free as we get up to wider band and these directional antennas. And one of the nice tools that we're developing is a ray tracer, which will allow us to use a physical environment, outdoor, indoor, put it in, and it'll help reduce the number of measurements we make. But we do have the measurement equipment here, and our industrial affiliates at NYU Wireless are constantly talking to us. We're helping them. They're asking us to measure things If your company's interested in joining NYU Wireless, we would love to have you provide data, all of our access to our students, all of our research is given to our affiliates before the world ever sees it. And we do a lot of work for our affiliates. You're basically stockholders in our center. So the ray tracer will become a tool that our affiliates can use as well. And this will help us figure out what's happening. There's another issue in terahertz and even in mmWave today that was never a problem in earlier generations of cellular. And that is this idea of spatial consistency. You see, in channel modeling, the world of wireless has always considered simulators to figure out their path loss and their coverage and their capacity by generating a channel state and taking that channel state and assuming over a local area that phases change uniformly. And they really haven't had the problem of doing the kinds of things that 5G will require, which is beamforming, beam search, diversity base stations. When we go up to these multi-gigabit per second data rates, we're going to have very short time intervals in which we have overhead to do the control and beamforming, and then we want to carry as much payload as possible before we recalibrate the channel. So the question becomes, what happens as a mobile at high speed, say at 100 kilometers per hour, is moving with tens of gigabits per second data coming to it? Well, you can travel over several meters while getting huge amounts of data, and we want to be able to have a very accurate channel model that can model the transients as you move over a local area. And we call this spatial consistency. Channel models today really don't have the ability to implement successive sample functions that very accurately recreate the impulse response. At NYU Wireless, we have a track. We've measured the channel, we have the data, and we're implementing that so that you can really understand the channel both from an omnidirectional and directional sense, and directional is more important as we go to terahertz. How does the channel change with a directional antenna? Does the directional antenna move out of the, if you will, spatially consistent region of the channel or not? So we're investigating that so that we can implement in simulation these tools, these channel models that can accurately allow the industry to build algorithms and build the phi and Mach layer techniques by having an accurate channel model. So there are spatially correlated large-scale parameters, delay, spread, shadow, fading, and there are also small-scale parameters that are spatially correlated to a local area. And 3GPP has decided arbitrarily it should be 10 to 15 meters in urban microcell. That's the standard body for the 5G cell phone new radio that's being implemented today. But it really is going to depend on the correlation distance of large-scale parameters, and you only know those if you measure them. Fortunately, we've measured a lot of this. We have huge amounts of data, and one of my master's students is going through that data, and we have this NYU Sim channel simulator that's a drop-based channel simulator. We've got over 75,000 downloads. We get dozens of downloads a day. All the major companies, research universities are using NYU Sim, and they're basically using this to study the channel. And we want to implement spatial consistency. And here's an example of some of the many measurements we have where we've measured in downtown Brooklyn the receiver moving around a corner. We capture the impulse response at all these locations, the angle of arrival, time of arrival, the entire channel, and in 3D. And then we're able to see what happens. And you can see at the receiver locations, as you go around the corner, you go from a line of sight to a non-line of sight, the multipath extends greatly. Here you can see the time delay becomes greater as we go around the corner. And so we're using this data to build a spatial consistent model. I only have a couple minutes, so let me finish off real quickly with some other ideas that some other colleagues in NYU Wireless are working on. As we go up to terahertz, we've got, as I mentioned, huge distances potentially, and we saw that what's been measured to date. And this is where we think the bands of interest are going to be. 140, 220, 340, 680. And what's fascinating is once you start to get up to these huge bandwidths, you basically can do edge computing and cognition. We're basically having enough data where you could send the information needed to do decisions, brain information. You know, huge decision making can be sent over the air where you can have remote decision making for major functions. Some of the big power challenges are, of course, the RF sources for power efficiency. Gas, GaN, indium gallium arsenide will be potential solution, and the ADC and baseband processing, where we have low resolution signal processing is what we want, because I'll show in a minute, you have lower number of bits in your analog to digital converter, you get much more power efficiency. Now, we're going to need adaptive beamforming, directional sensing, and the other thing is we're going to need to do is combat these end-to-end effects of channel intermittency if someone walks in front of the channel. Fortunately, the standard is such that the end-to-end channel intermittency is not going to be a problem unless you really have a deep shadowing event, unless something really dramatic happens. I don't think end-to-end intermittency is going to be that much of a problem. It's pretty easy to solve. But you know, getting the power efficiency and getting the beamforming to be able to work is really important. Now, the holy grail, the optimal situation is to have an all-digital, fully digital terahertz transceiver. We have done a lot of work on hybrid beamforming, and hybrid beamforming is likely to be used for the next decade. Hybrid beamforming is much more power efficient. You don't lose much at all in spectral efficiency compared to full digital. But eventually, maybe a decade, maybe 15 years from now, fully digital will be great to have. And our job at NYU Wireless is to be looking at things 10 to 15 years ahead. So we're looking at the idea of having a fully digital beamforming array where you can have multiple channels simultaneously operating on the same antenna with individual beams formed very specifically for each of those channels. Now, if you could do that with low resolution ADCs, as I'll show in a minute, you really can start doing better than today's hybrid beamforming systems. It becomes more power efficient. But that's tricky. You can only do that if you use low resolution. And this formula, P equals CF2B, is well known to be the power, its ratio of power consumed by an analog to digital converter. There's also many other challenges, but what's really interesting is if you look at the 3GPP standard, they give you about 20 milliseconds in order to form the beams. And right now, in 5G new radio, I wish they wouldn't have done this, but they did it. You basically are going to look at one sector, and then another frame you look at another sector, one frame you look at another sector. You know, if we implemented, you could have even done this hybrid beamforming, you could have done it all in 1 second. In one sector. So you could have done one 20 millisecond block and looked all the way, but they don't have that in the 5G new radio. So you're going to have a little bit more latency to find the antenna when you go into a deep fade. Fortunately, 320 milliseconds is not going to be that bad, but it is a little bit bad for driving speeds. Actually, it's a lot bad for driving speed. For pedestrian 5G new radio, we'll be okay. Someone blocks in the way, we'll still find another path. But you'd really, if you could have done that all digitally and had it done in one 5G new radio burst, you could have done it in 26 milliseconds. And when you get to 26 milliseconds to finding and fixing on the new beam, you can really start recovering from any kind of deep fade. Here's what's really fascinating. If you look at the power consumed in milliwatts for analog and hybrid, analog is just one channel. So this is just one channel. Hybrid would be for multiple channels. And if you do fully digital at 8 bits and 4 bits, look at the total power consumption. You can start getting fully digital for 16 channels, 16 receiver channels, less power consumed than one analog channel. That would be amazing. That would be amazing to get 16 channels less than one analog channel today. Well, to do that, we're going to have to be able to make things work at 4 bits or less. And you could do sigma delta ADCs and actually get even more equivalent bits. There are ways to do this. But what's exciting is if you look at the transmitter, even at the transmitter, you get huge power advantages if we could ever go fully digital with relatively low resolution. So we looked at both high and medium. This is Sandeep Rangan and some of his team looking at power levels. And what's fascinating is an all-digital implementation actually could be more power efficient than hybrid if we can make it work with low resolution. And that's the challenge. That's a great research area. It's a real digital signal processing research area. Now, some of the problems with low resolution is you'll never be able to exploit the high SNRs, that great resolution would give you. But you don't really need super high SNRs as long as you're getting the bit error rate that you want. Another problem with low resolution is you have relatively low side lobes when you do filtering, because you don't have a lot of resolution to get deep side lobes. However, you've got directive antennas. So the directive antennas will help, along with the low resolution, to push this out of band below what digital signal processing alone will do. These are exciting areas. It's been published last year in Asilomar, but it's an important area for our industrial affiliates. Understanding blockage, we've done a number of works in blockage, a number of students, number of faculty. So we're understanding the dynamics. And we've also made an NS3 module that a lot of our industrial affiliates are using, where we're able to implement kind of an open source end-to-end model for adaptive antennas, channel models. You can put NYU SIM into this. And we're working on building a Terahertz module. By the way, if you look at the lecture today at the NYU Circuits Symposium on Circuits, Terahertz and Beyond, you'll see that Joseph Jornet has an NS3 module end-to-end for terahertz. Fascinating. So universities were supposed to keep things open source. We like doing that. And once you have these link layer and physical layer models, the kinds we're developing here at NYU Wireless, you can then begin looking at end-to-end performance. So let me conclude by saying this mmWave coalition is important. I'm hoping this presentation can generate more interest, more involvement from our industrial affiliate sponsors. This is a wide open area. The spectrum is huge. There's a lot of work happening, as you'll see in the NYU Wireless seminar series. Here at NYU Wireless, we have a couple of very large projects. We have Comm Center, where NYU is the systems lead, with Sandeep Rangan as part of a $21 million SRC project to look at terahertz systems, devices. And then Professor Rangan and myself are on a NIST contract looking at public safety communications and using drones and some of these high bandwidth video applications for public safety. In conclusion, I want to thank all of you for being on the call. Thank you for being in the room. Great thanks to our industrial affiliates, and I just learned that AT&T is rejoining, so we'll have the AT&T logo up there shortly. And if your company is not a member, we hope to have you involved in our center soon. Thank you very much.